Dear students, today we can discuss three problems. The first question is show that first countability is a hereditary property. Solution, let x2 and yu be topological space. Actually, you have to prove that it's a hereditary property. First countability is a hereditary property. For that, we have to show that first this particular property, that the first countability is a topological property. Then you have to show that it is a hereditary property. For that, let x2 and yu be topological spaces, and suppose that x2 is first countable. Let f from x2 to yu be a homeomorphism for taking. You have to prove that yu is first countable. Okay, so taking a point y in y, since f is on to, here f is on to, therefore the x is x in x such that f of x equal to y. Here x2 is first countable. This implies x2 has a countable local basis at x. Put b dash is equal to set f of bn such that n and n. Then b dash is a countable collection of open sets in yu such that y equal to f of x. It's an element of f of bn for all n. And we are taking v as an open set containing y in y. That is v in the topology u and y in v, which implies f of x is in v. Further, f is continuous at x. This implies that x is a neighborhood u of x in x2 such that f of u is subset or equal to v. And now x in u and u in 2. This implies that x is basis element bn in b such that x is an element of bn subset or equal to u. This implies f of x is an element of f of bn which is subset or equal to fu, subset or equal to v. That is, y is an element of f of bn subset or equal to v. Note that f of bn is an element of b dash. Hence, b dash is a countable local basis at the point y. But y is arbitrary. That means capital yu is the topological space yu is first countable. Or we get that first countability is a topological property. Now, you have to consider a subset or equal to x. That is, hereditary property had a problem. That is, a space, a particular property shared equally by a space as well as every subspace of it. That is what a hereditary property. So, topological property you have proved first. And you have to prove that this is a hereditary property. That is, you have to prove that a to a is first countable. At a point a in a, an element a in a, this implies a in x. Here x2 is first countable implies there is a countable local basis at this point a, that is, say, b. You can call it as b. At b equal to collection of such bn such that n and n. Take b dash equal to set a bn intersection a where n is n. Then b dash is a countable collection of open sets in a to a such that the point a is an element of bn intersection a for all n. Let u in to a and a in u. U in to a implies u equal to v intersection a for some open set v in to. Thus v in to and a in v. Here b is a local basis at a in x2. Therefore, the x is basis element v in b such that a in bn which is subset or equal to v. That is, a in bn intersection a subset or equal to v intersection a, which implies a is an element of bn intersection a which is subset or equal to u. Note that bn intersection a is an element of b dash. Hence, b dash is a countable local basis at a, but a is arbitrary, and thus it follows that a to a is first countable, hence first countability is a hereditary property. That's all about the first question. The second question, show that second countability is a hereditary property. What is all at x2? Here again you have to show that second countability is a topological property first. Then you have to show that it is a hereditary property. Show that the second countability is a hereditary property is a question. You considering x2 and yu be two topological spaces. Suppose that x2 is second countable, f from x2 to yu be a homeomorphism. Since x2 is second countable, there exists a countable basis for x2, say b. What is b? Collection of such bn, n in n. At b dash equal to f of bn such that n in n. And b dash is a countable collection of open sets in yu. Let v in u let v in u and let y in v. This implies there exists x in x such that f of x equal to y. Here f is continuous at x and f of x is in v. Therefore there is a neighborhood u of x in x2 such that f of u is subset or equal to v. Now u in tau and x in u. This implies there exists basis element bn in b such that x in bn subset or equal to u, which implies f of x is element of f of bn which is subset or equal to f of u, which is subset or equal to v. This implies small y is an element of f of bn which is subset or equal to v. Hence b dash is a countable basis for yu, or yu is second countable. For second countability is a topological property. The next take a subset or equal to, which is a subspace. You have to consider first to prove that the a to a is second countable. As x2 is second countable, there is a countable basis for x2, say b. Let b equal to collection of bn such that n in n, and b dash equal to bn in the set of bn intersection a such that n in n and bn element of b. Then b dash is a countable collection of open sets in a to a. Here u is an element of to a is a point in u, then u equal to v intersection a for some v in tau. Now v in tau and a in v. Then there is a basis element bn in b such that a in bn subset or equal to v, because b is a basis. That is, a is an element of bn intersection a subset or equal to v intersection a, or a is an element of bn intersection a subset or equal to u. Note that bn intersection a is an element of b dash. Hence b dash is a countable basis for a to a, or a to a is second countable, or second countability is a hereditary property we have proved. The third question is, show that separability is not a hereditary property. You can prove it. Let a equal to, you are taking a as a set of xy in R2 such that y equal to 0. Clearly a is uncountable. Take capital X equal to a union set interval 0, 1. Define tau equal to set of u in px such that u equal to 5 or 0, 1 in u. Then tau is a topology on x. Now we show that x2 is separable. Let d equal to set of 0, 1. Clearly d bar is subset or equal to x. Result 1. Let xy in x and u be a neighborhood of xy. Then u in tau and u not equal to 5, or 0, 1 is in u, or u intersection d not equal to 5. Hence every neighborhood of xy intersects d, or xy is in d bar, that is capital X is subset or equal to d bar. From 1 and 2 we get d bar equal to x. From 1 and 2 we get d bar equal to x. Or we are getting d is a countable dense subset x tau. That means x tau is separable. Let a subset or equal to x. Now we show that the subspace topology tau a is the discrete topology on a. For that, let a0 in a, we have set a0 equal to set a0, 0, 1 intersection capital A. Note that set a0, 0, 1 is an element of tau. This implies set a0 is in tau a. Hence tau a is a discrete topology on a. If possible, assume that A has a countable dense subset D1. You can call it as a D1. This implies D1 bar equal to A, and D1 is countable. Since D1 is a subset of tau A and tau A is the discrete topology, we get D1 is closed. D1 is closed means D1 bar equal D1. Hence D1 equal to, actually D1 bar equal D1. We have already got D1 bar equal to A. Therefore D1 equal to A. A contradiction to A is uncountable. Hence our assumption is wrong, which implies A has no countable dense subset, or A tau A is not separable. Thus we have completed 3 problems here. Total 8 pages notes also given together with this. Go through the notes properly, listen the video file, and any confusion means we can discuss in the class.